All right, let's have a go at this. Change in position. There's a way to symbolize that. Now that we have a law, I would call that a change in, there's two conventional symbols in physics. For a change in position, we use R or S. Now, when we get to vectors, we'll have X, Y, Z. You can have a change in X, a change in Y, a change in Z. But when we generalize, we typically use one of two letters for a change in position, and it's either delta S or delta R. Not to be confused, the R is not to be confused with radius. Those are just conventional symbols that you'll see in every physics textbook out there. All right. So I'm going to use delta R for change in position because position has so many R's in it. And it starts with P. Therefore, the sensible letter is R. Reason we don't use delta P is the symbol for momentum. I just work here. The reasons for these letter symbols are due to men who wore wigs and tights several hundred years ago. It's their fault. All right. Do I need to say more? All right. Sometimes the letter makes sense. Sometimes it don't. So here's our identity for the change in position. But we also have a change in time. So delta T. At least our letter makes sense in that regard. Now, the independent variable is the one that we use in its quotient identity form. That's what I'm calling it, fancy form of 1, so that we can get the change quantity of position set up for the relationship with the change quantity of time. It's a blind date. We're setting them up, trying to create a hookup here for these two change quantities. So we bring that fancy form of 1 into the picture, and at this point, all we've done is preserve the identity on the dependent variable. That's all we've done so far. But given that axioms encode for what laws describe, we need to bring that independent variable into relationship with the dependent variable. Now we have an axiom that encodes for what the law describes. A change in position always requires a change in time. A quotient relationship is a this per that relationship. A little bit of this is always associated with a little bit of that. Isn't that what we determined when we said every change in position requires a change in time? A little of this always means a little of that. Now, does anybody know what we should call delta R per delta T? What? Which one is it? Nope. Velocity. Think of it, a change in position would be measured in a length like miles, and a change in time could be measured in hours, so miles per hour. This is you driving. You do this every day. So that it is what we call speed. All right. I'm going to use the letter V because if I give V a direction, then I have velocity. Velocity is a vector quantity, has magnitude and direction. But when I use V without the vector symbol, the little arrow over it, that means I have a speed. All right. You essentially have distance equals rate times time. That's the college algebra word problem version that you knew before you probably even came to college. You knew that distance equals rate times time. That's just one of those facts that people carry around. But we just built what I call the first zeroth law. Why do I call it the first zeroth law? Well, there was this dude named Newton he already took the first, second, and third laws of motion. And given that he's sort of important and I'm not, I have a zeroth law. But when I and my counterpart stumbled into this realization, we very quickly found that, well, there's not just one zeroth law. There's actually two zeroth laws. So we have a first one, and one would expect if there's a first zeroth law, there's at least one more. Whether there's 3 or 10 more, there's at least, if you have a first zeroth, the expectation is that there's a second zeroth law. All right? Otherwise, you wouldn't use first zeroth. You'd just say zeroth law. Like we did for thermodynamics. The zeroth law of thermodynamics came after the first law. We're like, oh crap, we need to have another one to precede this. Okay? More on that later. All right. So let me ask you a question. Is it possible for this thing here, speed, can that be a change quantity? Yeah. You've done this plenty. Let's stick with the car analogy. Your car will obtain a speed, and you are able to change its speed, assuming your car works. All right. So every change in speed, is there something that every change in speed requires? Every change in speed requires time, doesn't it? It's not like your car can instantly go from 40 to 60. It always takes time to change the speed of your car, whether it's speeding up or slowing down. So guess what? Every change in speed requires a change in time, and the same two-way street occurs, but every change in time does not require a change in speed. So the structure of the next zeroth law, the second one, is identical to the first one. Every change in speed requires a change in time, but not every change in time requires a change in speed. So guess what we do? We would end up writing every change in speed requires a change in time, which means my change in speed is always related to a change in time. And what do we call this construct right here, delta V per delta T? We call it acceleration, which would have been the hint here. And so here I have the second zeroth law. So before today, I think you knew that a final amount of something would always be equal to an initial amount of something plus the change amount. And these amounts are about the same something or other. Right? You could have figured this out before college. Basic idea. It's essentially sum of the parts equals the whole. The right-hand side being the parts, the final amount being the whole. Another idea you didn't need to come to college. You already knew it. So let's take these super duper basic ideas that essentially everybody and their dog that can fog a mirror knows and connect it to what we just did. All right. So let's think about let's say that my final speed, well, that's a pretty crappy color there. My final speed would equal my initial speed plus my change in speed. Right? This would be true. We could start our lawmaking game here. It wouldn't matter what the quantity was. Would it? It would matter whether it's force, energy, everything I could think of in science I could always write a valid equation by saying the final amount of it equals the initial amount of it plus how it changes. All right? Where the interesting part of the game is right here. What's the nature of the change? Newsflash, calculus is only about how stuff changes. It's the mathematics of change. Newton invented it to do that. The mathematics of his day wasn't powerful enough to help him describe his theory of motion and gravity, and he needed to account for changes better than anybody else had before, so he invented it. He was 23, a couple years off at the farm because there was a plague in Cambridge, so, you know, the easy life. So I think I'll invent a whole world-changing math system, all right? So what's the nature of the change? That's all physics and ultimately calculus is about. And so what did we determine? Well, we determined that the change in speed was equal to acceleration times time. So we go from here to here. That's what we just did in the last screen. This whole lab was about what's the nature of that change, but we came at it from the other direction. So if we were to continue from the direction we started, we would be moving up. We would just expand delta V into V, minus V naught equals A delta T, and that would just give me V equals V naught plus A delta T. I'd arrive at this the same way, or I'd get the same answer for a different reason. I purposely started with a concept, brought in what we just discovered, and realized that what is this equation actually telling me fundamentally? Well, it's telling me this, something I already knew. So in one sense, I'm giving you a lecture on the structure of physical law. Well, not just one sense, that is exactly what I did. And we're going to do this process over and over and over again. And as we get higher up in the food chain, forces and energy, it does get more complicated because there's more change variables. But you're still just pushing around symbols arithmetically, according to proportionalities and or the connections, and then you sort them and put the right name labels on them. That's the game.